Welcome to EDU World Space.
I'll begin by reading this problem. So you're told that an overhead transmission cable for electrical power is 2,000 meters long and consists of two parallel copper wires, each encased in an insulating material. A short circuit has developed somewhere along the length of the cable where the insulation has worn thin and the two wires are in contact. As a power company employee, you must locate the short so that repair crews can be sent to the location. Both ends of the cable have been disconnected from the power grid. At one end of the cable, call it point A, you connect the two ends of the two wires to a 9-volt battery that has negligible internal resistance, and you measure a 2.86 amperes of current flowing through the battery. At the other end of the cable, you attach the battery to those two wires, and you measure 1.65 amperes of current flowing through the battery. And we're asked to find how far is the short from point A. So I've given a diagram here, but we're given right away. We're given the length. We're given the material, so it's copper. The wires are in contact somewhere, so that's what the short means. We have EMF, a battery with negligible internal resistance, so it will put out 9 volts. And one end we call A and one end we call B. And so let's say the current at A, which I'll call IA, is 2.86 amperes, and the current at B, which is IB, is 1.65 amperes. And it's nice to have a picture because it kind of helps you to get oriented. So this green line is the insulating material, and this red X is a short. So the insulating material has worn out. So when you actually put a battery over here, your 9-volt battery over here, like so, you have a current that's flowing through this circuit. And the wires, they act as resistors, right? And it depends on the length. By this equation, R is equal to rho L over A. So you have a current that's flowing, and this end is open, so no current will flow here when you have the battery connected this way. And now if your battery is disconnected from here, so let's disconnect the battery. And now the battery is connected to this side, your 9-volt battery, then your current will flow in this particular fashion. And it won't flow through this end because this end is now opened, right? And this is the only point of contact because there's insulation throughout the rest of the wire. And what I've also done is divide the wires. I segmented the length. So this portion where you have the break in the wire from A to the break, I call LA, and from B to the break or the short point, I call LB. And obviously, the total length is the sum of the two segments, and the total length we're already given is 2,000 meters. So, how do we solve this particular problem? Well, one thing to note is that we have the voltage is equal to IR, right? And we know V, it's the same for both of them, right? So it's the same 9 volts. So VA, let's call this A. And we have another right for A and B. So VA and VB are equal to each other. VA is equal to VB, which is equal to your EMF, which is the 9 volts, right? Because we're putting the battery there, we neglect any kind of internal resistance. So the thing that's causing the change in the current now is the resistance of the wire, right? Which depends on the length of the wire because it's the same type of wire, but the length is changing, so the resistance in the wire is changing. So we're going to use these two equations together along with R is equal to rho L over A. So where the resistance is equal to the resistivity times the length of the cross-sectional area. So let's get to the next page and continue with our solution. So VA is equal to VB, and in general, we have V equal to IR. So then I have IA RA is equal to IB RB. And IA I know, and so I'm going to write R as, we also have R is equal to resistivity, length over cross-sectional area. So that's LA over cross-sectional area. Technically, there should be two LA because when the current makes a round trip, so it travels LA in the top wire in one direction, and then it travels LA again in the bottom wire. Once it reaches the short, then it goes back to the battery by traversing another LA. So it has to be 2 LA for the total length that it travels over the cross-sectional area, which is the same for the wires because we assume that they have the same diameter. So let's leave that as A, which is equal to IB times 2LB over A times rho. And it's all copper, so the resistivity is the same, the area is the same, and all of that cancels out, and the twos also cancel out, so we're left with IA LA is equal to IB LB. And so we want to find how far the short is with respect to the point A, with respect to side A. So we can eliminate LB by using L is equal to LA plus LB, which gives us that LB is equal to L minus LA. And I can plug that in here for LB, so I have IA LA is equal to IB times L minus LA. So now we know IA, we know IB, we know L, and all that remains is to find LA. So you can rearrange this equation to give you that LA is equal to IB over IA plus IB, all of this times the total length. And when you plug in the numbers, you get that. Let me refer back to the numbers here. So you have IB, which is 1.65 over IA, which is 2.86 amperes plus IB 1.65 amperes, and all of this times 2 times 10 to the 3 meters. And when you plug in those numbers, you get 731.71 meters. That's the answer.